Everybody okay with that so far? Okay, now let's talk about contactors. A contactor is basically what we have is we have a large coil and a large chunk of metal. We turn on the coil, which is an electromagnet, and it attracts the metal bit, and the big piece of metal moves, and that also closes contacts, which is how a contactor works. Now when we turn that coil off, the big piece of metal moves again, which opens the contacts. Now that's all well and good, except for the big piece of metal has been magnetized. So now we have a magnet which is moving. That magnet moves past a coil. When a magnet moves past a coil, it creates voltage, it creates electricity. The amplitude of that voltage is proportional to the rate of change of magnetism. So in other words, the faster the coil moves, the faster the contactor moves, the more the voltage will create. Now, when a contactor opens, it opens in very short time, in milliseconds. So we have a magnetic field which is moving very fast past a coil. The upshot of that is a great big electrical spike is sent from the contactor. Here's a contactor. A big electrical spike is sent from the contactor into the PLC. Now the very last thing you want is electrical spikes arriving in your PLC. A couple of ways we can get round this. One way we can get round this is by sticking a diode across our input, and then the spike freewheels around the diode and it doesn't necessarily go into the PLC. That's one method of stopping spikes getting into your PLC. A much better method of stopping spikes getting into your PLC is to stick something between the contactor and the PLC. And by that I mean, what we do is we stick a relay. We stick a relay between the contactor and the PLC. It's called an interposing relay. Interposing means it gets in between. So we stick a relay between the contactor and the PLC. Now, if there's any nasty spikes come from the contactor, they just end up in the relay, which is fine, because the relay costs, what, $5 max? So the worst thing that's going to happen is you're going to blow up a $5 relay. That's a lot better than blowing up a $4,000 PLC. Because what will happen is, if spikes get into that PLC, it jumps on the tracks in the PLC, and it will blow a hole in the PLC or blow the tracks out in the PLC. So if we use interposing relays in between our digital outputs and our contactors, then we will protect our PLC. And as instrument people, you need to protect your PLC at all costs. Now it turns out that using interposing relays is not only a good idea, but AS3000 actually says that we really should be doing this. AS3000 says that there must be segregation. Segregation must be maintained between low voltage, which is less than 1000 volts, and extra low voltage, which is what we're using in the PLCs. AS3000 says we must segregate PLC signals, extra low voltage signals, from low voltage. We must segregate in every way. There are exceptions. If you want to go, hang on, if I go to the next diagram. This is what AS3000 basically says. If you have a PLC, within your cabinet, you must have extra low voltage territory. And within that extra low voltage territory, that's where we'll be dealing with our 24 volt values. Everything in our extra low voltage territory will be 24 volt, our signals basically coming in, our 4 to 20 milliamp signals and that sort of thing. Outside of extra low voltage territory, that'll be low voltage territory. Now that will be things like contactors and other nasties. What we have is we have interposing relays, and they're the border guards, so that our digital DOs, our digital outputs, will go through the interposing relays and from there to the contactors, so that we have low voltage outside and extra low voltage inside. As far as the extra low voltage goes, not only does the PLC need to be in extra low voltage territory, but also the signals coming into the PLC and the signals going out of the PLC must also be in extra low voltage territory. If you need to take a 2 volt 40 volt signal into your PLC, you need to bring it in separately segregated, which means in a piece of, say, flexible conduit. If you've got a PLC which needs a transformer, the transformer has to live outside of extra low voltage territory. If you've got a PLC which is running on 240 volts, you need to bring the 240 volts in on a little bit of flexible conduit which will come into the PLC, and it will be like a little intrusion. That flexible conduit will maintain segregation. If you need to go 24 volts out into low voltage territory, you are allowed to do that if you're either in conduit to maintain segregation, or if you use signal cable which is capable of taking the voltage and the current that is available out there. What that basically means is you need to take your 24 volt signal through. If you need to take a 24 volt signal in, it has to be basically in TPI, double insulated and thick enough to take the voltage and current that's out there. So if you're happy to terminate everything in TPI, that's fine. But it's not actually easy to terminate TPI onto tiny weeny little PLC terminals. Now, AS3000 states that we must maintain segregation. A lot of people seem to think that this is some sort of optional rule, that if the enclosure is not big enough, we don't have to do this. We actually do have to do this. We have to maintain segregation between the 24 volts and the 240 volts. If nothing else, it's a good idea because it's protecting our PLC from the nasty 240 stuff. It's protecting our PLC from noise. Hopefully, on the jobs you're doing, you're seeing segregation maintained. How are we doing with that? Do most people see segregation, or is it a bit of a joke? Well, I'm actually delighted to see that most places it's maintained. It really does need to be maintained. What we're doing is we're trying to protect our signals from noise. We're trying, well, AS3000 is trying to protect our signals from blowing up the PLC, but by maintaining segregation, we're maintaining segregation from noise. And it's not just segregation within the enclosure, of course. It should be segregation on the ladder, in the conduit coming out. Now, I know what it's like. If you've got to run a piece of cable in, you look up at the ceiling, you see a ladder, then, you know, or a piece of conduit, you're going to run your signal in that because it happens to be going the right way. But really, we need to make an effort there. I don't know if I've previously talked to you about inputs and outputs. There are two ways of inputting and outputting. Some of you, this might be a repeat, but it actually bears repeating. There are two ways of inputting and outputting. The first way, which I like to call the sensible way, because it's the way anybody with a brain would do it, is that you switch 24 volts. 24 volts is switched. So out in the field, there are switches which switch 24 volts. And when the 24 volts appear on the input switches on. What that means is if you check your input with your voltmeter, if you have 24 volts on that screw, that means it's on. So 24 volts is switched. It's called syncing because on the input screw itself is actually connected to, via all this wiring, is connected to a sink. So the input screw itself is at earth potential until you put 24 volts on there. So it's syncing. Output is called sourcing. The output is called sourcing because once again we're switching 24 volts. So the output screw is the source of the 24 volts. We switch the 24 volts and we go out to the load, and on the other side of the load is a return to earth. The other side of the load is the sink. That's the sensible way of doing inputs and outputs. On the other hand, we have the American way of doing inputs and outputs. The Americans like switching returns. They also like switching neutrals, which is something we have to be aware of. Now, the Americans like to switch returns. What that means is the input is called sourcing because the input screw itself is at 24 volt potential. And we switch it. When we switch the return, the earth, the input screw goes down to 0 volts. So if you're testing this with your voltmeter, 24 volts is off, 0 volts is on. This is the American system. They like to switch returns. It's called sourcing because the screw is the source of the 24 volts. The input screw is the source of the 24 volts. Similarly, they switch 24 volts inside. They switch return inside the PLC. This time it's called syncing because the PLC output screw is the sink. It's the earth path. What this means is the load is permanently powered. The load always has 24 volts on it. It's permanently powered. And we are supplying an earth path in the PLC. Now, have I gone through this before with you, or is this the first time I've mentioned it? Okay, so you all appreciate that the American system is incredibly dangerous. Just be aware that it's out there, and you may be seeing it. Now, PLCs, typically on a PLC, there's going to be a couple of screws. I'll get a better colour than it. There's going to be a couple of screws on the PLC itself, which will be marked 24 volts and return. That's because the PLCs all have a little power supply on board. It's a marketing exercise. It uses one of those bloody awful little rectifiers, and it's there just so that the PLC people can say, yes, we supply 24 volts. Never ever actually pull power out of a PLC. If you pull power out of a PLC, if you pull much more than like 1/4 of a pufteenth of power out of the thing, you will cook the PLC board. It's as simple as that. So you never use a PLC power supply. All you'll do if you do that is you'll cook up the PLC. What you should use instead is you should use an external power supply. One of those nice gold brick type power supplies. So they're biggish bricks inside a metal case, and they've got screws on the front, 24 volts. And you use one of these and you make sure it has what's called crowbar protection. I'm not exactly sure what crowbar protection is supposed to mean, but to my mind it means it should protect it if somebody drops a crowbar across the inputs. Basically what happens with crowbar protection is, if the inputs are shorted down to earth, the power supply switches off. So you'll get called in at some point because everything's stopped working, and you'll get your little voltmeter, digital voltmeter, and you'll attach it to the 24 volts and you'll see nothing. Now what you do to reset crowbar protection, typically you unplug it and plug it back in. So we got a plug. So we unplug it, we plug it back in, and the voltage comes back 24 volts and then almost immediately drops away. That's a sign that the power supply is protecting itself. What you now do is you now go and work out what's wrong. So you'll have a whole bunch of instruments on the 24 volt supply line, and they'll all go off. And what you do is you disconnect all the instruments, pull the plug out, plug the plug back in. The 24 volts should come back because it's not drawing any load from anywhere. And then you connect the instruments back up one at a time until the voltage goes away. And then once the voltage has gone away, you know that the one that you just connected up must be shorted to ground. So you go along and you go down the conduit, you find where the conduit fell off and the operators have been gnawing on the cables. You beat the operators back, using a cross and a wooden stake and stuff. So you get the operators back, you fix up the cable, you put the lid back on, and then you go and reconnect everything, and it should all be good. Oops, should have done that in white. Still should have done that in white. So, and it should all be good, and the thing should connect up, and we're all good to go. Of course, there is the slight problem that when you unplug and plug stuff back in repeatedly, quite often just doing that tends to blow it up. So you may find that in the course of this you accidentally blow up your power supply. Well, that's no big deal. It's only a $400 power supply. It's better to blow up a $400 power supply than a $4,000 PLC. So that's the power supply on a PLC. Never use it. Now, one thing about the gold brick power supply you buy, the nice power supply, it must be an extremely polite power supply so that it gives out 24 volts in a straight line. 24 volts, no nasty ripples, no nasty transients, just a nice 24 volt DC output with no transients. If you output any type of ripple to virtually to instruments, what you will do is, within most instruments nowadays, there's little boxes, and these little boxes are called DC to DC converters. And what DC to DC converters allow you to do is they allow you to take 24 volts and change it into plus or minus 15, or 5 volts, or even 300 volts. And a DC to DC converter is a small black piece of silicone pot with legs sticking out the bottom. A couple of legs on the front and 2 legs on the back. If you give a DC to DC converter any type of transient, any type of AC, the DC to DC converter will blow up. When it blows up, it kind of expands and it smells absolutely outrageously disgusting. So you must make sure that you have a nice, polite 24 volt, or you will blow up the instruments. Well, not blow them up, you will stuff up the instruments.